everyone. Welcome to episode number 659 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Are you ready, my friends? We are headed to the highest highs and the lowest lows this week. From way up in the skies to the deepest oceans, this week's podcast covers it all. First up, my guest is Paul Barnard from MathWorks. Paul and I are chatting all about one of my favorite topics, advanced air mobility. Paul and I chat about the biggest software development challenges for AAM vehicles, the benefits that modular software can bring to these kinds of designs, and how engineers are aligning simulation models with real-world flight data. Also this week, I check out SeaClear, a EU project that utilizes a team of autonomous robots to collect waste from the ocean floor. But first, let's bring in Paul from MathWorks to talk all about advanced air mobility. Hi, Paul. Thank you so much for joining me.
Yeah, happy to be here.
Excellent. Okay, so let's talk about advanced air mobility vehicles. Now, as advanced air mobility vehicles move toward commercial viability, what key challenges are engineers facing related specifically to the design of software systems?
Yes, well, one of the biggest challenges I see or we see in this space is really that the business model isn't yet settled on the advanced air mobility. We have a great technology idea, and a number of companies are pursuing this. The idea of electrified, autonomous, vertical, and horizontal flight capabilities. But what will be the most valuable business case for companies to pursue? Will it be more compared to grabbing an Uber in a city, or will it be more compared to the cost of flying a helicopter today? Really, that business model, I think, is the key challenge that's driving, some of the back and forth in this, and really is the key to coming up with the right commercial viability for these systems. An example I'll give is it going to be the right business model to fly people from city center to city center? Or is a better model to fly people from a satellite airport, maybe to a large city international airport to jump on another flight? These are the questions that are really in the mind of a lot of the companies that are developing the advanced air mobility systems. The second thing I'll mention is there really is no history on these vehicles to build upon. They're all very unique designs, unique configurations between rotors and wing-borne flight. And so we don't have a lot of people in the industry with years of experience and wisdom to design a new vehicle like this. And furthermore, even the certification authorities are trying to keep up with where this area is going. So it's a very exciting time. There's a lot of potential, but really trying to get the business model worked out will take some time as we move toward commercial viability. And I think that presents a key challenge to a number of engineers.
So, Paul, what does the modular software architecture look like in practice for these kinds of vehicles?
Yeah, the modular software is really required for these vehicles, and it's due to the fact that the vehicle configuration and the capabilities are evolving as the business models emerge. So really having a flexible software architecture is key, since the whole vehicle architecture may evolve as the designers and engineers work to seek out the most commercially viable missions. So flexibility is key. It's driving the modularity. But because these systems also will be certified as flight worthy, there also must be rigor in the design and in the verification process. And so to meet this challenge, many teams adopt a modular software architecture. It allows engineers to isolate and verify pieces of the system as individual subsystems. That might be a flight control subsystem. It might be an autonomy subsystem or a propulsion subsystem. And they can do that isolate and verify while postponing the full system configuration decisions that are still being worked out as the mission changes. For example, you might take an architecture designed to support both tilt rotor and multi-rotor designs, and then use previously qualified modules across different vehicle types without having to start from scratch. So the modular systems and the modular architecture can be updated and retested as the overall system configuration evolves. And that's critical for compliance when changes occur either mid-development or even maybe later in the development cycle for these systems.
So, Paul, how are engineers ensuring traceability from requirements to test cases, models, code, and artifacts?
They are doing it primarily by centering their development process on models. And this is really what we call model-based design. It's when the model covers the system level behavior as well as the software behavior and design. And so in model-based design, you do your design work while simulating the overall system with a dynamic model. That model forms an executable specification which communicates far more to various teams than a static document would. Also, through automatic code generation technology, you can generate the embedded code that is programmed for flight critical functions like rotor control, stability systems, or other flight management functions. And doing all of this with simulation and testing of the models early allows you to shift left the testing and verification. This is a huge, huge advantage because it's well known and documented that if you find errors early in your process, they're much easier and less expensive to fix as compared to finding problems during flight testing or programs farther downstream. So what we talk about is try to do more testing on the desktop and less in the lab. Try to do more testing in the lab and less in flight test. Basically moving things early. We're not trying to eliminate any testing. We're just trying to do it as close as possible to where errors in requirements or design might be introduced. And that makes any errors less expensive to fix. So with model-based design, you can easily form a digital thread to document the traceability from requirements down to the software code. And this is accomplished because the model becomes the source of truth for the code. And through that automation, you can trace requirements down to the code.
All right. So, Paul, how do modular software architectures support certification in practice?
So basically, the modularity allows for certifiable workflows where the components can be independently verified and tested. Now, certification workflows require robust and repeatable testing strategies. That's a key element with them. And by doing early system verification, you can build repeatable tests very early in the program lifecycle. And doing that at the system level lets you incorporate real world effects, such as weather, wind, or other aircraft that might be in proximity to a particular scenario. Now, a good example of this is a detect and avoid system for AAM, and using simulations to test the autonomous functions that you may need to do things like recognize other aircraft, to take evasive maneuver, or maybe to replan a route to avoid a collision or avoid another conflict. So automated testing of the algorithms at this level supports the regulatory expectations for consistency and documentation while enabling engineers to catch interface mismatches or timing issues or other types of errors, could be errors in the requirements, and finding those well before integration and flight tests. And furthermore, many organizations are now adopting CI/CD servers for continuous integration and test to support agile and continuous testing workflows with models.
So, Paul, in these AAM programs using digital twins, how are engineers aligning simulation models with real world flight data?
Digital twins are used to align and tune a simulation to a real world system. It might be the aircraft that's built, or it might be a certain particular model number of an aircraft. In the case of AAM, the goal would be to have either an engineering simulator or a motion-based simulator that is as accurate as possible, and it becomes the twin to the actual flight vehicle. Now, the process of aligning these is one of matching a digital simulation to real-world flight test data. Optimization methods are applied to the data that comes from a flight test, and then the simulation is mathematically tweaked until the simulation matches the real-world data. Usually, this involves back calculating parameters like aerodynamic coefficients or propulsive effectiveness in an accurate way, and then tuning that to match the real situation. Now, these values, as an example, they aren't always easily found in isolated testing. So the installed real-world performance of a rotor or a motor or some type of aerodynamic system can be slightly different. And this is why the alignment is important to create the most accurate digital twin. Another great example is you could do the same thing as an aircraft ages. For the case of an AAM vehicle that is powered by a battery, we know that batteries degrade over time. It would be important to know the battery health of a particular vehicle so that things like range of the aircraft or payload capacity could be predicted accurately for a particular vehicle. And it might be that the mission vehicle can handle changes over time. And so it would be important to use a digital twin for something like that as another example.
So, Paul, how do you think engineers are balancing model fidelity with simulation runtime and scalability?
The answer really is that it is a balance, and it's one where the fulcrum of the balance moves back and forth depending on what you're doing. You really should only simulate with as much fidelity as you need to answer the question you have. And so it becomes an important task of an engineer to make sure that the simulation has the right fidelity for what they're trying to do. It's easy to build models with lots of fidelity and lots of detail, but then you may have scalability issues. So being able to flexibly go back and forth different levels of fidelity is really the most effective way to use simulation. So you can get the right answers for what you're trying to figure out with a particular simulator. One great way to do that is to use different variations of a simulation. You might have a detailed model of an electric motor for a vehicle, and that detailed model is important for really confirming the performance of a motor, of a rotor system. But then you might have a very simple model of that same motor that's used when you're ready to run a simulation with 500 or 1,000 Monte Carlo runs looking at different scenarios across a flight envelope. So it's very important to be able to move back and forth along a spectrum of fidelity and scalability and to have the flexibility to do that.
That makes sense. All right, Paul, it's time for your off the cuff question. So, Paul, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Oh, that's a great one. I would have what I would call a proper steak dinner, a nice steak dinner with vegetables, baked potato, and probably a filet mignon.
Yes, what a good choice. All right, well, I think that's all I have time for today. Thank you so much for joining me, Paul.
Great. Thank you, Amelia. It was a great conversation.
From high in the air to the deepest parts of the ocean, my friends. Have you heard about the SeaClear project? So, SeaClear, which stands for Search, Identification, and Collection of Marine Litter with Autonomous Robots, is an EU initiative. Now, the goal of this initiative is to find and collect waste from the ocean floor with the use of a team of autonomous robots. The original project ran from 2020 to 2023, and a follow-up project, SeaClear 2.0, is currently in progress, with its focus being on larger debris and deeper waters. So, the SeaClear system is super cool. It's designed to operate without human intervention and includes several different components. First, there's an unmanned surface vehicle, or USV. This is the mothership. It's the central hub for the system. This hub provides power, computational resources, and a deployment platform for the underwater robots. Then there is a UAV, which can be used in clear water conditions to scan the surface and surrounding areas for large pockets of litter. This system also uses two unmanned underwater vehicles, or UUVs, which includes a smaller observation robot called Mini Tortuga, which maps the seafloor using cameras and sonar, and also uses AI to differentiate between litter and marine life. There is also a larger collection robot called Tortuga with a custom designed gripper and suction device that can retrieve the identified litter and then deposit that trash into a collection basket that is lowered from the surface vessel. So, the trash collection process first starts with that unmanned service vessel that uses ultrasonic waves to create a preliminary map of the seabed. Then, a dedicated search robot conducts more detailed scans of the depths. This data is then transmitted to that gripper bot, which is then deployed for object extraction. There are also autonomous dinghies that can also function as surface level collection points as well. Now, the trash identification part is really interesting. So, the SeaClear system uses onboard sonar, a sensor camera, and AI processing to locate and identify seabed debris suitable for removal. Now, the AI's purpose is to recognize the trash, which can range from old tires to car seats to fishing nets and even bicycles, and determine the optimal grip point for the robot. Now, given the scarcity of image data for training AI to classify and identify underwater debris, right? The SeaClear partners compiled over 7,000 images during their various testing phases. These objects were then converted into 3D models for further use. So, the SeaClear 2 project is going strong, with the ultimate goal being fleets of automated robo teams taking on the arduous task of cleaning up our messes in the ocean. And folks, I'm here for it. So, if you'd like more information about SeaClear 2 or more information about how you can use MATLAB and Simulink for aerospace certification standards compliance, or even to watch videos about designing a battery system for a VX4 eVTOL aircraft, or a model-based approach to emulating eVTOL aircraft, I've included a bunch of links below the player on this week's Fish Frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon too. And we also have a YouTube channel. Yes, we do. It is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series hosted by me and our animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EEJournal. For the week of November 21st, 2025, I'm Amelia Dalton, and you've been fried.